So today we're going to start our discussion of vectors, and today we're going to be looking at vectors in the plane specifically, so two-dimensional kind of things. Very quickly we're going to move into vectors in space, though, like I think it's Wednesday even, okay? So to start with, just a little bit of development of the idea. So to describe, the velocity of a moving object. We need to specify both its speed and direction. We represent such a quantity graphically by a directed line segment. And that actually looks like a ray, okay? We denote the directed line segment extending from the initial point P to the terminal point Q by PQ. An arrow on the top, and of course you'll notice that looks a lot like ray as well. We refer to the length of PQ as its magnitude and that is denoted with double bars around it like this. Mathematically, that word's not going to fit on that line. We consider all directed line segments with the same magnitude and in the same direction as equivalent. Regardless of their initial point. And we use the term vector to describe any quantity that has both magnitude and direction. Might be the most writing I've done in one chunk in here. I don't know, back in section 10.6 or 10.5, I wrote a lot too. So one of the things that this says is that we have things that are called equivalent vectors, but they don't necessarily start and end at the same spot. They have the same length and they go in the same direction, but they're not actually starting and ending the same place. So if we had, visually speaking, that was terrible because that's dotted. Let me see. If we have this line segment, directed line segment, and I'll put an arrow on the end to indicate the direction. And I'm going to do a copy paste just so that I can move it without making sure I don't change anything. And I moved it over here. These two would be equivalent. Okay? Same direction, same length. All right. So the first thing that we're going to take a look at doing is actually creating a vector given an initial point and a final point, or a terminal point. So our directions are just that. We're going to find a vector. Oh, let me say it that way. Example. With initial point A and terminal point B. And A is going to be 1, 1, and B will be -2, 4. And the way that we find a vector is by taking, there's a couple of ways we can write them, so I'll write it in this direction first. Our vector can be written with sort of the brackets that look like less than and greater than symbols on the ends of them. And we take the terminal point minus the initial point for the ordered pairs, and we do it, pairwise. So I would have -2 minus 1 for the x component. I would have 4 minus 1 for the y component. And then if I simplify that, of course, I have -3, 3. That's one way to designate a vector. Okay, so it's component-wise. Tells you how far you go in the x direction, how far you go in the y direction. And we'll go ahead and graph this just so that you can see why that visually makes sense. So I should have used my grid. Let me do that real quick. So if I were to plot the initial point and the terminal point, so here's 1, 1, and then I had -2, 4 right here. So if I were to connect these with a line segment, I should use the one that looks like this. Okay, so there's my directed line segment. And if I were to do the same thing, but I would have used like the -3, that I just created. So you would start with the origin. This is actually resetting it back in the origin, and it tells you go left 3. That's what the x coordinate tells you. And you go up 3. So -3 would put me here. And again, if I were to connect that with a directed line segment, you can see they're parallel, right? They're the same length in the same direction. So they're equivalent. That's what we're creating. We're creating, or we sort of, you can think of it as resetting the initial point to the point 0, 0, or to the origin, and you're showing the direction from there. Okay? Another way to write our vectors, oops, let me switch this back to my lines. Another way to write the vectors is in IJ format. You see that in physics, right? So IJK, but we're not to space yet. So what are the I and the J? They're the X and the Y values. So which is which? All right, so if you would imagine that instead of the, or in relation to the x-axis, we have the direction I going along with x and the direction J going along with Y. And yeah, when we get into space here in the next couple of days, we'll be having IJK. Then another way to write this, and you'll see your book use these interchangeably, is to write this as 3I plus 3J. Okay?
Are those subscripts or just?
They're not subscripts. They're written almost like a variable would be written next to it in terms of size. You'll often see them emboldened too when they're typewritten, like they look like they're bold shaded instead of just being like a script for a variable or something like that. They look like they're bold. And what they are, yes, you can
think of factors, think of them as one north and one east.
Yeah, that's a good way to describe them. They're unit vectors is what they are. They're unit vectors in the left-right direction or in the north-south direction. East, west, left, right would work.
It's like -3 times 1 north.
Yeah.
So it's basically the same thing that we've been doing here.
Quite possibly. Yeah. Yeah, quite possibly. Sounds like.
Or the I is like a factor this way.
Yes. Yeah. Same idea. Yeah. Okay, so there's two ways that we're going to focus on them being written. You're going to use them interchangeably. Your book will write them in sometimes in the first one, though sometimes they'll write it in the second direction. I think we're ready for the next example. Any more questions on that one in terms of that? Okay, so what we're going to do next is I'm going to show you how we add and subtract vectors, how we find magnitudes of vectors, and I'm also going to show you how those look visually, like if we were to graph them. I decided I didn't really care that you graphed a whole lot of them in terms of your homework, but I do want you to see the relationship when we graph them together, okay? So take a look at this example with me. We're going to find quite a few things. We're going to compute, and these actually look like they're boldened too when you see them, like, because your vector, I'm not going to do it that way because they look funny, but we're going to compute the vectors A plus B. I'm going to give you a vector A and a vector B here in a minute. A minus 2B, 3A, the magnitude of 5B minus 2A, which I haven't shown you how to do magnitude yet, but I will. And we're going to illustrate like a drawing, if you will. A plus B and A minus B. In order to do that, I better give you an A and a B. So this is example number 2. A is the vector 2, 4, and B is the vector 3, -1. Okay, so these are not ordered pairs. The last example I gave you, I had ordered pairs, an initial and a terminal point. These are actually vectors, so we could draw these vectors. They both start at the origin and they extend on the first one to the right 2 and up 4, and the other one extends to the right 3 and down 1. And we'll draw them in a minute, okay? But these are two vectors. These are not ordered pairs. However, everything that you want to be true is true, okay? So when we take A plus B, what would you want to be true? That you just add them component-wise, right? And you do. It actually works. So we would have 2 plus 3. We would have 4 plus a negative 1. And so the result would be what? 5, 3? Yeah. What do you think would happen if we did, what did I have the next one as? A minus 2b. What would that, reasonably speaking, be?
2 minus 6b.
2 minus 3b. I'm sorry, 2 minus, the 2, and then 2, and then the 3 here is what I wanted to do. Sorry, yes. Yeah, 2 is a scalar. And then we would have 4 minus, and then we would have 2 times the y, or the second value in the, or the, yeah, the y value or coordinate basically in the b vector, which was what? Negative 1. Okay. And what would we get? Negative 4 and positive 6. All right, what do you think 3a would be? Yeah, you just multiply each of them by 3, so I have 6, 12. Okay, just increases the length of my vector, right? Okay, the next part, we're going to do it in 2 pieces. The first thing I'd like to do is to do 5b minus 2a, okay? And then I'll show you how to find magnitude, because I haven't actually shown you how to find magnitude at all, but you'll recognize it when I do, and you'll be like, oh, I've done that before. You just didn't know it was called that before, okay? So what would I do to find 5b minus 2a? 5 times the b coordinate, which was 3. Wasn't it 3? Yeah. Minus 2 times the a value, which was 2. Or the x coordinate in the a. And then I have 5 times negative 1 minus 2 times 4. So 15 minus 4 would give me 11, and negative 5 minus 8 would give me negative 13. Okay, so think with me for a moment. Let's actually draw the vector 11, negative 13, or you can just watch me to draw that, that's fine. If I were to draw this vector, I don't have any of my lines anymore, hang on. Uh, 11, negative 13, I need space over here. So it's going to look something like that. How could I find the magnitude? Remember, magnitude is length. How could I find the length of this? Distance formula or Pythagorean theorem. Yeah, that's what you're quoting, right? That's all magnitude is. Okay, it's just the distance formula or Pythagorean theorem. So if I'm finding, which is the actual part this question asked me about, which is 5b minus 2a, what I really want is I really want the square root of 11 squared plus 13 squared. One of them was negative. Which one was it? The 13. Not that it matters, but I'll write it in just for the sake of saying it did. So what is 11 squared plus 13 squared? David's got his calculator out, so we'll let him tell us. Huh? 290 is right.
293?
290.
Oh.
Sure, good guess.
293?
Yeah, good guess. Yeah, 290, which actually doesn't simplify either. I mean, we could get it a decimal approximation, but we'll leave it in exact form. So square root of 290 would be our magnitude of 5b minus 2a. So the last piece that we were actually asked to do here was to visually sort of draw what this looks like if we do a and a plus b and b. Okay, so I want to take a graph and we'll do that. Let me delete this graph that I've got down here and I'll put back my grid on. So I want to draw in my graph, and I'd like for you to as well. Go ahead and draw the graph of a and the graph of b. And we actually know a plus b because you have it, but hold off on that one for a moment. Just draw in what a is and what b is. And remember, they start at initial point at the origin, and they extend to the terminal point being the length, or not the length, but the terminal point is the vector itself. So a is 2, 4, should be here. And then B is 3, -1, which should be here. Whoops. Okay, so we already said that all the vectors are the same if they're the same length and they're parallel to one another, right? Same length, same direction. So what I'm going to do is I'm going to take that vector I just drew in B, and you can take yours and transpose it with, I know you can't cut and paste, but I'm going to take mine and cut and paste, and I'm going to move it so that it's starting at the end point where A ended.
Wait, if we're dealing with 5B minus 2A?
I'm not. We're doing A plus B.
Okay.
This is not part D. It's, if you will, part E, which is to draw these things graphically. I'm on the point right here. Okay? So I've got A, and I've got B here. And that's equivalent to the B that started at the origin, right? And ended at 3, -1. Now, A plus B is what? It's ending at that same point, right? So if I put my vectors end to end, and it doesn't matter which one I started with, it's commutative just like, A plus B, which I'll show you some properties here in a minute, but A plus B is the same as B plus A. This is actually, whoops, change the color is what I wanted to do. This is the vector A plus B. So if I put the vectors end to end from the addition, this is what I end up with. Okay, so this is A plus B. Let's do the same thing for A minus B. So what I'd like for you to do again is to draw in vector A. We'll start with vector A. I'm going to give yourself a little bit more space over here. So A went 2, 4. Yeah. And now I need negative B. Well, we know what B is, right? It's this piece here. So I could calculate negative B, correct? Sure, no problem. Negative B would be -3, 1. So I'm going to do the same thing I did before. I'm going to go to -3, 1, which would be here, and I'm going to transpose it here in a moment too. So here's my vector B, negative B, and I'm going to move it up here. I don't think I drew that very well. Let me try that again. Okay. It would be right here. What did I not do right? Okay, I'm not doing a good job transposing. I'm just going to draw it from scratch here. It should be 3 to the left and up 1. That's where it's supposed to be. Agreed? Everybody's good with that? Okay, I don't know why my transposing is not cooperating, but it's not. And so if I were to add those together, right, A and negative B, I would end up with the same vector that I would get if I did A minus B. And I don't have it actually written there. I wasn't asked to calculate that one specifically like I was asked to calculate A minus or A plus B. But visually speaking, here would be my A.
I think it'd be -1 and 5.
Yeah, it would. Mm-hmm. So here's A minus B. So here's A, and here's minus B, and then I've got A minus B. Okay? Sound good? Very cool. You good?
Just talking, yeah.
You're okay. All right. So I want to show you some properties. I mean, we've already said that the things that we want to be true are true, and there's a theorem that actually says that more formally. So I'm going to do that for you next and show you the things that are true really are true. And these are properties now of vectors. So this is theorem 11.1 is what your book calls it. And the first one is that A plus B is equal to B plus A. And that's called what? That's the commutative property. So commutativity. There's another one. We'll see if you guys remember the names of some of these properties. That says if you have A plus B plus C, it equals A plus B plus C. Do you remember what that property is called? Yeah, it's the associative property, or associativity. How about A plus 0 is equal to A? You know what that one's called? Yeah, it's the additive identity. And of course, that 0 would be the 0 vector. It's got as many zeros as you need in there, right, for however big your vector happens to be. In our case, we're just doing 2 by 2 vector, or a 2-dimensional vector instead of 3-dimensional, which we'll get to. A plus negative A is equal to 0. Additive inverse. Number 5. I need to identify for you, so to write this down, but then I need you to write something else down afterwards about what these letters represent. Okay? D times A plus B is DA plus DB. You know what the property is. What's the property? It's a distributive property, but I need you to identify real quick that this D is a scalar multiple. Okay, it's just a number. So D is an element of the real numbers, whereas A and B are vectors.
D is just a scalar?
Yes, it's a scalar. Okay, so we're not multiplying vectors here. That is not what's happening. We will, but not today, right? That's a much more complicated question. So this is just, it's like scalar multiplication is what we were doing before, and so these are with scalars. So this is the distributive law. And it works the same way. I'll write the other one in here. It's technically called number 6 here, but it works the same way if I had A plus B as vectors times D on the other side, right? So I have the ability to distribute on either direction or in either direction. So it's just the distributive law again. 1 times A is A. What is that besides true? That's the multiplicative identity. And 0 times A is 0. It's a 0 property. And as I'm even writing this down, I don't know that I checked to make sure that your book actually called those last two what we wrote them down as. That's what my last book called them, and so I didn't actually check on that. Sometimes I'll slightly change things, but it works. It's a 0 property, right? And multiply by 0, you get 0. All right, so let's take a couple other avenues in talking about these. We talked about magnitude and how to find it. So we're going to do another example that has to do with magnitude. So, I'm sorry, did you get everything written down? Did I move too fast? My apologies. Got it? Okay. So let's take an example where we're looking at magnitude and we're going to do something else with it. We're going to, A, find the magnitude. Of our vector V. And then B, we're going to find a unit vector. We haven't done that yet. In the direction of V. So I inadvertently, not really, but it just sort of happened. I used the words unit vector before without really identifying what they were, but some of you already knew what they were because you started it. What do you suppose unit vector means? Yeah, a vector with magnitude 1. So essentially what we're going to do is we're going to take a vector that has an undetermined or like an arbitrary, is what I really want to say, an arbitrary length, and we're going to scale it back to being the same direction, but it's going to be of length 1 specifically. okay? And here's how we do that. We need to find the magnitude. So even though this is sort of written as part A, part B, we couldn't do part B without doing part A anyway.
It's
Ethan?
very complicated, but I believe that what you're doing is the hypotenuse has to be 1, and then you have to find the I and J coordinates.
That's exactly right. Yeah, that's exactly right. So the one that we're going to look at, the vector, oops, I didn't write that down yet. The vector V we're looking at is going to be 2I plus 4J. Okay? So part A is to find the magnitude of V. So how do I find the magnitude of V? Great. Square root of 2 squared plus 4 squared, or 4 squared plus 2 squared. 2 squared plus 4 squared is what? 20. So this is square root of 20. And if I were to simplify that without approximating it, yeah, 2 square root of 5. Okay, so that's the actual length of this current vector. So let's imagine just for a moment that you had a nice value, and the value of your magnitude was 5. What would I have to do to get this thing that's of length 5 to be a length 1? I need to divide by 5 or multiply by the reciprocal. So this is an ugly number, right? It's not 5, it's 2 square root of 5. But what we're going to do is we're going to take this exact vector that we already have, component-wise if you want, or written in the IJ form, I don't care. And you're going to, I'll leave it in the IJ form. And you're going to divide it component-wise by the magnitude that you just found. But you guys know enough to know that we don't leave radicals in denominators. We don't leave fractions unsimplified and so forth. So my fractions simplify first. That's kind of friendly. And then what am I going to do about the radicals in the denominators?
Just multiply square root of 5 by root of 5.
Yep. Multiply the top and the bottom by square root of 5. So this is square root of 5 over 5I plus 2 square root of 5 over 5J. And this would be a unit vector, same length as we had before. Not the same length, same direction as we were in before, as I meant to say. Yeah. And it's of length 1, right? Because it's a unit vector now. Okay. Let's do another one that has to do with magnitude. I think I have space enough to still write on this screen, so let's give it a shot. We're going to find a vector R with the given magnitude in the same direction as U. So I'm given a vector U, and I want to find another vector of a specific length, but in the same direction that U is already in. And what are I on? 4. My magnitude of my vector V is going to be 10, and my vector U is 3,
Right, vector
1.
V, vector U.
Oh, R. I think I meant to put a V there. Oh yeah, I was looking at something else. Okay, just change the R right here for V. My bad. My handwriting's not the best apparently on my other sheet of paper today. Yeah. Oh, and I didn't finish my notation. Okay. So this is very similar to the last problem. I've got a vector. I want it in the same direction as the vector I already have. But I don't want it to be a magnitude of 1. I want it to be a magnitude, in this case, of 10. So any idea about what I could do to make that happen? Okay, I do need to multiply by 10 eventually, but I need to do something before that. David?
Divide by the magnitude of U.
Yeah. And what good will that do me?
So that gets you unit vector.
All right, so if I could take what I have and turn it into a unit vector, then I could do like, oh my word, seriously? Becca is what I wanted to say, and then it felt like that wasn't right. What Becca suggested, which is then to multiply it by 10, right? Then I would have it in the same direction because it was already created that way, right? Because I started with the unit vector was given, or the vector I was given and made it a unit vector. And then it will have length 10 because I've multiplied by 10. Okay, cool. So let's actually take a look at that. So how do I get this to be a unit vector then? Yeah, I need to find the magnitude of, in this case, u. So 3 squared,
Root 10.
1 squared, square root 10. So if I want the unit vector in the direction of u, then I would have 3 over square root 10. And what was my other number 1? 1 over square root 10. And this is not really an a and a b, I've kind of made it like that, which would be 3 square root 10 over 10, square root 10 over 10, right? That's the unit vector in the direction of u. And then what would I do to actually find the vector that I want, my new vector? Yeah, I'd multiply by 10. So 10 times 3 root 10 over 10, root 10 over 10. So I would get 3 root 10 root 10. Ethan?
I'd like to skip something between finding the magnitude of 3 root over 10 and 1 over root 10. Because we already know what the unit vectors for u are. So why are we changing them?
No, I don't have a, we want a unit vector in the direction of u.
Oh, so the 3 and 1 is just the direction?
The 3 and the 1 gave us the direction, right? And it already had a magnitude of square root of 10.
Okay.
So if you think about it visually, what I
Wait,
have,
what do you mean? So I had a magnitude of square root.
You found the magnitude of u, which is square root.
yeah, 3, 1.
I think I connect those two.
So here was my original vector right here. And I scaled it back to be length 1. That's what I did first. And then I multiplied it 10 to extend it. It's a double scaling factor is all I really did. I scaled it back to be length 1, and then I scaled it up to be a length 10. Sound right? I think I said it right, didn't I? Okay, good. All right. One more example. You ready for it?
Can I leave those in IJ
Oh.
format?
Yeah, I don't care.
Okay.
I don't care what form you use, and your book's going to go back and forth between the two. So whichever one you feel comfortable or want to use, go for it. Yeah. Am I okay to switch my screen, Ethan? You're still typing. Okay.
Quick question, if it's
Okay.
magnitude root 10,
Uh-huh.
and then we're getting a new vector, we're doing it at times 10, does that seem right?
Yeah, it just happened to be the same on this one. There's
Yeah.
nothing about the fact that those would have had to be the same.
Your magnitude for b equals 10 becomes a scalar.
Yeah.
Okay. Because
So we
mag-
divided it by its own magnitude. It's just that happened to be that the magnitude was square root of 10, and our new scale that we wanted at the end happened to also be 10. Yeah. So typically speaking, this would in no way, shape, or form need to match that. That just was the way it was in this particular problem. I usually try to avoid duplications like that because I don't want you to think that there's a connection, and it kind of looks that way on this one, but there's not supposed to be. It does simplify nicely, however. All right, last example. We're going to find the vector with the magnitude and angle from the positive x-axis. The magnitude's 2. and the angle is pi thirds. So if the magnitude's 2 and the angle is pi thirds, this should feel like something we've done before. What does it feel like? Feels like polar coordinates. In fact, the book that I used before called it polar in this particular direction set. This one just didn't use it, so I tried to model my directions after theirs.
So
But
magnitude equals R. And just
yeah,
like that.
the magnitude is r, and this angle is the same theta in polar coordinates.
Just gonna do, okay.
Yeah, we're just going to do what? Go ahead. Do you remember? Somebody help him out.
I know exactly.
So what are my how did we do polar coordinates? Yeah, this is r theta to start with, but we want to write it in our rectangular form here, like the vector form we've been doing. Yeah. X is equal to r cosine theta, and y is equal to r sine theta. So we've got r is 2, cosine of pi over 3, and we have 2 sine of pi over 3. The question is, do you remember what cosine of pi over 3 and sine of pi over 3 are? Do you?
Cos is 60 degrees. That means cos is 60 degrees. And
It is?
yes.
I think we got 1/2 on this one, right?
Yep.
Is that right?
Sine is something complicated.
Something complicated.
Square root of 3.
Square root of 3 over 2.
Okay, so
Yeah. So my vector is actually 1 square root of 3.
Is that all we're finding?
That's all we're finding. We're just asked to find the vector. And our vectors right now that we're working with are all determined in terms of the x and the y direction of the initial point being at the origin and the terminal point being at the xy order pair. Yep. All right.
Best lesson all semester.
So I think you need homework. Oh, yay. All right. Page 755. 6, 7, 19, 20, 31, 34, 36, 37, 45, 48, 50, and 51. All right, I'll see you guys on Wednesday.